Hello everybody, welcome back to MSE100. So far what we've been doing in the course is looking at mechanical design, essentially, or mechanical drawings. So where we are looking at computer aided drawing or CAD, and then we're also concentrating on hand drawing of components, or which is known as engineering drawing, where we are focusing on different shapes, most of them being having straight lines, then how you project them, how you dimension them, and then how you convey that information. Since we are in mechatronics, you would also be doing some actually a reasonable amount of electronic design. Again, just as we talked about, you learning more about the mechanical design later on, later courses. Similarly, the actual selection of components and what various functions are and all of that stuff would be covered in circuits and more advanced courses in mechatronics. Nonetheless, what we're going to be focusing on is kind of at a level where we are assuming we somehow know what we're going to be designing, or we basically created a circuit, and then we're going to focus on creating what's known as printed circuit boards, or kind of like creating a schematic for those drawings and then convey that information. So that's what we're going to be focusing on for this week's lecture. So without further ado, so let's move to the sheet over here. So here is our learning objective. So we're going to review some of the electronic components. So although I mentioned that you're going to be focusing mostly on the design, you still need to have some background of electronics. So we'll do some quick review. I know some of you, or actually most of you, have done some basic electronics in your undergrad, excuse me, in your pre-undergrad, or some of you are taking this course later on, so you have some advanced background. Nonetheless, we're going to review some of the electronic components, and then we will solve some very preliminary or rudimentary problems in electronics. So it's more like an electrical problem, which would be encountered in electronics later on. So with that, so these are the things we're going to be focusing on. So we're going to be looking at the basic power supply, resistors, capacitors, inductors, and so on. So those are different electronic components. We'll be looking at diodes, and LEDs are light emitting diodes. And then we'll look at what is known as a full bridge rectifier. And then we'll talk about printed circuit boards, integrated circuits, and then some simple electronic components. And then we'll do a very preliminary, or kind of like a simple manual PCB design. That's the focus here. So there are a couple of useful links over here. So this is the Spark Fun, which actually has a lot of tutorials on basic stuff. And then you also have an e-log, which kind of gives you some circuits example, which is actually really nice. And then there are a couple of other things. So this link over here, so this is going to be giving you some background on operational amplifiers, and then we have the Wikipedia article on circuit diagram. So these would be kind of giving you some background, and I also have a link to a free book. I know it's a little bit outdated, but nonetheless, at the level at which we are dealing with, should be okay. So that's what we're going to be focusing on. So just some quick background. So we are going to be using, so these would be IEC standards that are used. So essentially when we have our schematics, so we can do one of two things. So our wires, so these are known as wires or traces. So you typically want to make, so if you have a connection, so you have one wire, and so because it's going to be on 2D, so we have, say, one wire here and then another wire touching it. So then what you want to do is you want to basically put a dot over here as shown at this point. So if you put a dot, that means those wires are actually in contact. So if you don't have the dot over here, or rather let's put a note. So this is wires or traces in contact. And then if you don't have a junction, so what you typically do is you kind of leave, so for instance, if you have two wires, so kind of like going on top of each other, so you're not actually touching each other. So in that case, what you do is you kind of put a loop. So this is known as trace crossing. So this is a junction, this is a trace crossing. So where you kind of put a loop on top of it, and then that indicates that the wires aren't in contact. So sometimes you notice that the wires will kind of go through straight, and then you don't have a dot over here, and so that's still considered to be crossing wire over here. So this is known as a trace crossing. Just a quick note. So this is in terms of the schematic itself. But if you're creating physical circuits, if you try to put one wire on top of the other, there's always going to be connection between them. So in physical PCB design, so you want to never have wires cross on top of each other because it will create a short circuit. So the other symbol that you'll actually encounter a lot is this symbol over here. So which is the either sometimes you'll have just like one line, or more often than not you'll have three lines. So this is known as the ground or the zero reference voltage in your circuit. So it's kind of like talking about the ground floor or the floor, and then you basically talk about the heights with respect to the floor. So that's the same concept over here. So the symbol for ground, and that's the reference zero. So if I put say plus y somewhere in my circuit, that basically means it's relative to the zero voltage that I have. So sometimes we also have triangle, downward facing triangle. So this is known as a signal or low noise ground. So this is useful when you're doing signal processing, where you want to denote grounds be as separate grounds, even though physically they might be connected. So this basically is the very basic concept that we'll be using, and then we'll start looking at different components in our electronic circuit right now. So the first component we'll be looking at is the DC power supply, or it's going to be the battery. So what happens is here we have a bunch of batteries, the most common ones that you see. So this one is a D cell. So this one is a C. This one is a AA, which is common, sometimes known as a pencil battery. This is AAA, which is actually a little bit smaller. And then you actually now have a quadruple A. So for instance, if I look at my pen, so they tend to actually use a quadruple A battery. So I have one battery over here. So this is actually a 9-volt battery over here. So this is kind of a Panasonic 9 volts. I'm actually not peddling Panasonic batteries, so this is the one I just happened to find it. So typically what will happen is you'll have a sign that's denoted. Let me angle it so that you don't have too much of reflection. So you notice there is a plus and a minus. So there is a minus on this side and a plus on this side. Then if you look down, these two look different. So generally what happens is this is kind of the negative and this is the positive. And so sometimes what will happen is you'll basically call this as the zero reference. So you might actually connect this point to the ground, where then this whatever voltage is going to be the positive voltage. So if you read, so apart from Panasonic, it basically kind of gives you other information. So it basically says there's a 9-volt battery over here, and then it kind of gives you other branding. So this is not much of concern over here. So what we do in that case, so is that irrespective of what battery it is, it might have different voltage. So this is a symbol that we use in our circuit. So where we have a longer line and a shorter line. So sometimes the bottom line is thicker, and sometimes you put the plus to denote the positive side. So even if the plus is not there, the longer line is called the positive of the battery. And then you have, so this whole battery is these two leads coming out is kind of the representative of the battery. So what this actually represents is you can think about some potential energy being stored in battery. So it's similar to if you have, say, the tank. If you look at the water tank in cities, maybe not in Vancouver, but if you go a little bit further out, you'll notice that tanks that store water, so that basically stores the energy, and then you can potentially use that energy to drive some motor or some other aspect where you're basically converting that potential energy to other form of energy. A more broader concept would be, so if we go to say so if you go to the Cleveland Dam, so you notice that the water is stored. So that's also kind of like a concept. You think of it as being a huge battery that stores a lot of potential energy. So in that case, the energy that you can actually extract kind of depends on the lower or the reference voltage. So what we can think about as this being the zero or the reference. So this basically acts as the power source in a circuit. So it actually provides all of the power in a circuit. And so what happens is this is analogous in hydraulics or water terminology, kind of analogous to water stored at a height. And then the current is basically the water flow, so the product of the two power that's consumed. So the battery again would be thought of as a reservoir of energy. So this is actually potential energy. So that's basically the height of the water that gives it potential energy. In the case of the battery, it's actually some form of chemical energy. Essentially, you have two compounds. So this is an alkaline, so it has an alkaline component in it. So what happens is those two chemicals actually want to react and release energy. And then what we do is not let them react directly, but rather we force them to drive an electrical circuit or an electric current in an external circuit, which allows us to basically draw the power from the chemical energy. So what we typically do is we can basically give this as a zero reference, and then we can kind of think about the potential energy in the system over here. So what we talked about is known as a DC power. So if I took a multimeter and then measure this value, so you notice that the voltage actually is constant value. So let's actually do that. What I have here, so if you look at this, so this device is known as a multimeter. So this actually can measure a lot. The reason it's called a multimeter is it actually can measure a lot of the components here. So then what we typically do is we kind of have two leads to it. So then don't worry too much about the multimeter itself. So I'm not going to ask you questions regarding that. So nonetheless, so what we typically do is it has, so if you look at this a little bit closer, so here it has the ground symbol over here. So that basically means that this is the reference for this multimeter. So if you want to measure some voltage, take this out and then be a little bit clearer. So it says it's the ground symbol over here. It also says common. And here it says V. Don't worry about the rest of it. So what needs to happen is if you want to measure some voltage, we need to use this as the reference voltage. So let's try measuring some voltage over here. So I'm going to select a range. So I'm going to basically select from 0 to 20 volts, the 20 volts range that I select. And then I have two batteries over here. So this is the AA battery. So what I typically do is notice if I connect black one, which is connected to the 0, then I connect the red over here. It shows about 1.34 volts. And then if you look at the battery, it kind of gives you different standards. And then it's supposed to be a 1.5 volts. So this battery is probably a little bit dead. So it's producing a little bit lower voltage. It's been slightly used. And then this one is what's known as a 9-volt battery. And then if I connect, so notice that if I connect the black to the ground over here, then the white or the red to the positive, produce about 9.49 or 9.5 volts. So notice that if I call the positive, so if I connect the 0, the black lead positive of the battery, so I'm doing this, might be helpful. If I connect this, and then if I do the other way, so what's actually happening is because I'm calling the highest voltage of the battery, the 9 volts, to be 0, so the negative is actually below, kind of like below that value. It's kind of like inside the ground. That basically means it's producing a negative voltage. So that's where the sign basically comes from. And you can do all of that stuff, and then you can do kind of like other stuff with the battery. So you can connect these batteries in series, or you can connect them in parallel to produce more current. You connect them in series, you produce a higher amount of voltage over here. So let's get back and look at the next voltage that next type of power we're going to be looking at. So that's known as the AC power. So far what we did is we looked at a DC or a direct, it's known as a DC or a direct current, where the voltage actually remains constant. And then if you also have a thing known as an alternating or an AC power, so where if you look at all of your wall circuit, so this is obviously recorded in North America. This is our circuit over here. So if this is printed in your notes as well. So you actually have a note where it says this is the AC power, and these are actually standardized for each country and each continent. So in North America, we basically use what's known as a 110, 120 volts. So it changes a little bit from one place to another, and then it's a 60 hertz signal. And so what it actually happens is we basically would take a plug of the sort. So essentially, it has one is a little bit smaller than the other, and then I can basically just plug it into the circuit. So obviously, the bigger one goes into the bigger thing over here, and then if you kind of like look at your nodes, basically one is called as a hot, the other one is called as a neutral. And then this one is the ground, which is used to kind of like, so if there is any short circuit and it prevents the current and electricity from flowing through a person, rather it basically flows through the ground and then flows away from shocking or creating too much of an destruction over here. Nonetheless, so what actually happens is our symbol, or the if you took an oscilloscope, which is a device that actually measures the waveform, and then I advise you not to do this, but if you happen to put it in and then connect it very carefully and then measure the voltage across these two leads, you'll actually notice that it varies sinusoidally or as a sine function over time. And so what actually happens is you can take an average of this value. So obviously the average of this value is going to be 0, but you can do what's known as an RMS, which kind of measures the root mean squared. So you basically square all of these, take the mean and then take the square root. So if you did that, so you'll notice that these average, because this is higher, so you basically might get an average over something like this. So this is known as the RMS value or the root mean squared, or this is the effective voltage of the component over here. So the multimeter can actually measure these RMS values. So if I go back to the multimeter, so this actually has another segment over here, so it has 500 and 200. So if I happen to switch the circuit over here, this can actually measure the RMS value. So it just gives me a warning in this case saying very high voltage, be careful. 200 is still high, but it's okay. So I can potentially measure all voltage. So if I basically connected this, it actually doesn't measure battery. So if I try to connect and measure the battery over here, it cannot measure the battery voltage because it's not really sinusoid. So it kind of does some processing and then tries to find the average effective value based on the AC circuit. So it has so obviously you don't want like 120 volts going into the box. So what it does is it kind of like does some scaling down and then does the conversion. So then it finds the RMS value based on that. So if we come back here, so the AC symbol that we use is, this is the symbol for the AC circuit, where you have kind of like a sinusoid over here, which represents that it's a varying voltage or varying power. So what you can think about is, this is similar to maybe like water sloshing in the pipe, going back and forth. And so the water itself doesn't really move anywhere, but you can potentially harness energy from it, right? So you can think about the, so if you go, we don't have too much waves in Vancouver, but say if you happen to go, say to the Vancouver Island, and then you notice that there is a bigger amount of waves, so the wave goes in and goes out, or Vancouver, you have the tides coming in and going back. And so the water itself kind of just like effectively sloshes around, but you can potentially gather energy from it because of the way the water is sloshing. You can actually take some energy and then maybe have like a ratchet mechanism which kind of like move something, or you can basically convert that sloshing energy into another form of energy which will be used in electronic circuit. So nonetheless, so what happens is you'll notice that almost all of your component basically has a plug like this, and most of the power that comes in your house from the main is going to be an AC. So the reason I'm saying most of the power is there is some discussion on going into a high voltage DC grid. So they're more advanced. We probably don't have anything over here. Maybe if you went to a server farm or a server system, what might happen is they might actually do the AC DC conversion, or actually have like a DC grid in that local location or the local grid, so where everything is going to be direct current. So apart from those very strange exceptions, all of your power is going to be coming in as an AC voltage. And then you notice that a lot of your components, like say for instance your laptop, or actually even this multimeter, actually runs on direct current or DC power. So this one actually has a battery inside. I'm not going to take that out. So that actually has a 9-volt battery like this inside that actually drives the whole circuit. But for your laptop, what you actually do is you actually take the power, and you have the laptop brick, which kind of looks a little bit big, and then you do some signal processing and then try to convert this varying power over here, the varying AC power, into a constant voltage which can be used for your laptop. So this is kind of a little bit outside the scope. So the reason we use AC power is it's actually easier to transport AC power. So you can do something known as a stepping up or a stepping down of voltage, which is actually useful to minimize the power losses, and you can actually reduce the size of the wires that are used. So that's the reason we use AC, and it's also easier to generate and transport. That's the basic thing, and our power source actually drives all of the other components in your circuitry. So the next component we're going to be looking at is known as a resistor or a resistance. What the resistor does is it opposes the flow of current. So you think about the flow of current like a flow of water, and then it's similar to like a pipe having a restriction as over here. So what it actually does is it basically makes sure that water doesn't maybe go as freely. So it just makes a resistance or prevents water from moving freely through the surface. So what actually happens if you think about this is in the case of the water, as it flows through it, it actually loses some amount of energy. So similarly, when you have a constant current flowing through the resistance, it actually loses its potential energy. So we can actually write that. So since we know our voltage or the potential energy, voltage potential is denoted by V, and then the current is denoted by I. The equation here is V equal to IR. So this V is the voltage across the resistance, and then the I is the current flowing through it, and then R is the value of the resistance. So the symbol for resistance over here is ohm, and it's denoted by this letter ohm. It's ohm. And so this is the symbol, and this is the unit of resistance that we use. So you can actually connect resistance in series, so where you put one resistance after the other, or you can connect them in parallel. So think about this. So if you basically have two pipes, one after the other, so you basically are going to increase your resistance over here. And if you have two pipes in parallel, so what actually happens is that the current can actually flow through either one of the pipes. So effectively, you are reducing the resistance. So we can actually mathematically write that. So if you have, this is known as resistance in series. When it says series, it's one after the other. So the total or the effective resistance between this point and this point is going to be R1 plus R2, where R1 and R2 are the individual resistance. R1, this is R2. Total resistance is going to be R1 plus R2. If you have them in parallel, which is kind of like this is known as a parallel arrangement, the total resistance is going to be given by 1 over R total will be equal to essentially 1 over R1 plus 1 over R2. So you can actually rewrite this if you want, and then we'll see this shortly in the next case over here. So let's now look at some of the more common, or actually the common applications of resistance over here. So I've just picked two common applications over here. So here, so we have the first circuit on the top. So here, so where you notice that you have two resistors over here. So the first example is known as a voltage divide. So here you notice that there are two resistors. So let's label them R1 at the top and R2 at the bottom. So what's actually happening, if you think about, is that the current actually flows through the circuit, and what needs to happen is that there's going to be a voltage drop across R1, and then there's going to be another voltage drop across R2. So essentially you have a one voltage drop and a second voltage drop, and then based on some of the properties of electricity, so these two voltage drops need to add up total voltage. So this is actually known as Kirchhoff's voltage law. Essentially what it says is the total sum of all the voltages needs to add up to zero when you go through the loop. So that basically means that there is a voltage drop here and voltage drop here. So this is actually a voltage jump or an increase in voltage. So what will happen is this is going to be divided between these two resistances, R1 and R2. And then what will actually happen is that the voltage gets divided in the ratio of the two resistances. So it will basically be divided by ratio of R1 to R2. If we kind of do some manipulation, like mathematical manipulation, so you can actually show that the output voltage here is going to be equal to V in, which is this voltage, times R2, which is the lower, divided by the sum of the two resistances. So we can actually use this as a voltage divide. So you shouldn't actually draw too much current from this voltage divide. So as long as you don't draw too much current, then output voltage can be given by this value, and you can actually use this as a reference for another circuit. So this is particularly useful if your V in is known very accurately, then you can actually use this voltage divide. So you can actually rearrange or kind of like do the same thing, the same schematic in a slightly different fashion. So what you can actually do is call this point to be ground. So you can actually connect the ground to all that as a zero reference. Then what you can do is actually attach a ground to this point as well, and then just get rid of this connection. Because both of these are actually connected to the ground, it indicates that there is actually a connection between the two. So it's similar to saying, hey, this is going all the way and then going to ground, this is also ground, and then you're assuming all of the grounds are connected to one another. So the second example is what's known as like the application would be where you want to restrict the voltage that's applied. So we're going to basically assume maybe you have a battery that's supplying, say this is a 9-volt battery. So assume you're supplying a 9-volt battery, and then you have a device downstream, or you have a load that I've denoted here, for which you know the voltage and the current that the load will actually consume. So somebody tells you that, so this is maybe like not a resistance, but a more complicated circuit, maybe something else, maybe your cell phone, which, say for instance, if you have a USB, so this actually needs a 5 volts going into it, and then and then maybe somebody, you've done the calculation and you know exactly the current that's needed. So in that case, you can still drive the load using a higher voltage, as long as you actually add a resistance in series. So what will actually happen is we have to choose this resistance in such a way that if you know the load here, so you basically drop the V in minus VL at this point, so that the downstream voltage here is going to be equal to the load voltage that we need. So if you put a note here, so this is my load that I connect. So this basically takes a voltage VL and IL, and so that means that the IL is actually flowing through this point as well. And so if I connect and mark this as R drop, and then I can basically show that because the voltage drop here is going to be V in minus VL, and then the current is IL, based on the resistance equation, we can show that the R drop you need to choose equal to V in minus VL divided by IL. So as long as you can do this, calculate this value over here. So the other application is known as pull up and pull down. So I'll kind of like explain what those are. So what happens is sometimes, depending on the application, so some electronic components, they're designed in such a way that are actually required to connect a resistance to the output. So what generally happens is you have some components which if you don't connect anything to the output, it'll actually produce some random or white noise on the output, particularly some types of sensors. So what happens is, depending on the application and how the component actually works, so you need to either pull up the resistance. What we do in that case is we basically connect resistance to supply voltage. So what happens is, when the component is active, it will actually somehow work to lower the voltage. So essentially what will happen is the component is designed in such a way that it'll essentially, it's known as a current sink. So it'll start pulling current through the circuit so that it actually lowers the voltage when it's actually active. So just what we do is basically connect here to the top, and then this connects here. So this will typically be a very high resistance. And then if you do that, the output when the component is inactive would be basically equal to the voltage. When it's active, it will basically reduce, and so maybe you'll get a slip input or something else happens, and then you know that the signal output is non-zero. So you can actually process the signal. Similarly, there are other components which actually are current sources. So what happens in that case is typically a pull down resistance. So essentially what you do is you connect it to the negative of the battery. So I have the symbol here. And what you can do then is when the component is active, it actually increases the output voltage. So essentially it will be the zero voltage when it's connected. So you connect the ground over here and here, and then it produces a essentially if your signal, or it needs to output a signal, it will force the signal output to be non-zero value. So this is how you would use a pull up or a pull down resistance, and you don't have to worry too much about it. So typically information would be given to you, or whoever is making this sensor or this component will tell you, hey, you need to use a particular pull up or a pull down resistance. And occasionally they might give you some current range, or based on the voltage and the current requirement that you use, you might need to calculate the value of the resistance. But more often than not, they will actually even give the range of the resistance. Say just connected by like a 10 mega ohm resistance, 10 mega ohm resistance, and then there might be some occasional downstream calculation you would need based on the current you consume. There might be some small errors that you need to correct for in your circuit design. So next, we look at a component known as a capacitor. So the capacitor basically has the symbol of either like parallel lines or a parallel line with a curved line at the bottom. So these are slightly different. So this one is known as a normal capacitor. One to the right is known as an electrolytic capacitor. But they more or less function the same way. The only difference is if you have an electrolytic capacitor, you need to make sure that you connect plus to the positive of the battery. Otherwise, this is it kind of cause some damage to the component over here. So the capacitor itself, what happens is you actually have two parallel plates of conductors, and then you have an insulating material between the two. And so what happens is the current cannot actually flow directly between the two components, and what it actually does is it actually stores the charge between the two parallel plates, and then that's how it actually builds up energy or stores the energy in this case. So this might be analogous to a small like a tank in your connection. So what actually happens is as the water flows, the level in the tank actually rises. It's going to oppose any new voltage or new coming in. So this is analogous to a small size tank in your circuit. So what actually happens is that the symbol for the capacitance or the symbol for the capacitor is capacitance, and the unit is basically farad. It's little, the symbol is F, and typically what happens is you encounter the normal capacitance of a normal capacitor would be in the order of picofarads. It should be 10 to the minus 12 farad. 1 picofarad is 10 to the negative 12. And then you have this here, which is an electrolytic capacitor, which usually has capacitance in microfarad, which is 10 to the minus 6. So this is actually typically much higher, but there are some disadvantage based on application, so which might be discussed more in an electronic class. So nonetheless, all of the capacitances behave, or capacitors behave in the same way. So essentially what happens is the voltage across the capacitance, voltage across the capacitor is given by 1 over C, where C is the capacitance, times Q. Here, Q is the charge that's stored in the capacitor, and the V is the voltage across the capacitor between top and the bottom. In this case, you need, for the electrolytic capacitor, you need to have this to be positive and this to be negative. So if you can think about it, so essentially this will be the voltage that's dropped, and because the Q is the charge, which is so if you integrate charge, you can get current. So you can noting that the Q is the integral of the current. So you can actually write as the current I equal to C dV by dt. So if we think about connecting a capacitance directly to it, so what will actually happen is at the initial time, you're going to draw some current, and then as the charge builds up in the capacitance, the charge builds up in the capacitor, current drawn would start to decrease and eventually it'll exponentially go to zero. So typically what happens is this is the typical application. So essentially if you have say some device over here, the capacitor can actually smoothen out pulses. So what happens is if you have the capacitor connected in parallel to some circuit, obviously if you have a DC there's no pulses, or maybe the DC is generated by some other device. So if this pulse being generated at this point, the capacitor will actually store when there is a pulse voltage higher, it's going to store that energy, and then when the voltage drops below average value, it'll give out the energy. So what it effectively does is it's going to decrease the amplitude of the pulses over. The other use of the capacitor that's shown here is known as the low pass filter. So what it actually does is if you think about the circuit, have a constant voltage, it's going to just be outputted. But if you have a very fast varying voltage, current just passes through the capacitor and you don't actually have an output over here. Just to write it, voltage changes very slowly, V out will be equal to V in, changes very quickly, V out will be equal to 0. So that's the function of the low pass filter. So the next component we are going to be looking at is known as the inductor. So this is the schematic of the inductor. So the inductor actually stores magnetic energy. So it actually stores magnetic energy from the current flow. So essentially what is done is you take like metallic coil, and then you take wire which is typically insulated, and then you basically wrap the wire around the kind of like a magnetic coil or a magnetic. So because there is some basically it comes from Faraday's laws of electronics. So nonetheless, anytime you have a current that's flowing, it's going to cause some magnetic field that's created. And if you actually loop the wires very tightly, and then if you have a magnetic core, typically an iron core, which soft iron core, the magnetic field can actually be stored in that particular iron core. So an analogous to this would be like a paddle wheel or a flywheel in your circuit or your engine. So what happens is if you have a voltage or a current flow, the wheel actually has some inertia into it. So as the current is flowing, it's going to be rotating at its own speed. Try to stop. If you try to reduce it, it's going to start to pump some of the energy it's stored, and then try to pump and current the same constant. So the symbol for the inductor is L. This is the inductance. The unit is Henry. And the symbol is H. And in electronic components, typically you will encounter inductances in millihenry. But you can actually have higher inductance for your motor that actually has some windings in it. So they would have much higher inductance. And then if you have like a large transformer, those can have much higher inductance. But when we're dealing with electronic components, they will typically be Henry, which is actually on the higher side. So the voltage across the inductance is given by minus L di by dt. So essentially what it does is it's going to resist the change current value. So typical application, so you can basically have the circuit is closed, this one is open. What will actually happen is when you suddenly open the circuit, notice the current flowing through the inductor would suddenly drop to 0, then di by dt goes to infinity, so it can potentially produce an infinite amount of voltage. So what it can actually do, look at this closely, actually a spark that can be generated. Inductance is used as what's known as a ballast, or it can produce a very high like a high voltage to create a spark. So if you have an internal combustion engine, they actually used to use one of these. So they have an inductance, and then that will basically store the current, and then when you have a circuit that breaks the contact, and then when that happens, it's going to produce a very high voltage, which actually produces a spark between the spark plug. That's how you ignite the fuel. So now this is done electronically, but nonetheless that's the same principle that was used. So they also used in ballast. If you actually, the CFLs are being phased out as well, but if you happen to have a CFL, a compact fluorescent light, look at the bottom. So that's a bulky component that actually uses a ballast, which is used to kind of like ignite the or start the flow of current in the compact fluorescent. So the next component we're going to be looking at is what's known as a diode. So diodes are actually non-linear components. What that means is that the current is not always directly proportional to the voltage, or the voltage is not directly proportional to the current over here. So these ones are analogous to kind of like a flow control. So in that, so if I have the diode pointing in one direction, so in this case, direction of arrow kind of indicates, or rather the direction of this triangle kind of indicates the direction of the allowed current flow of the diode. So generally the way the diode is represented is by this triangle over here, line here, and this is the actual physical photo of a diode. And then you have a little white bar which denotes this cathode or the negative side. Typically what we want is that the plus of the diode or this side of the arrow connected to the positive, then this side will be connected to the negative or some downstream component. So if you flip the diode where the cathode is connected to the positive, it doesn't actually allow any current flow through the diode. So if we summarize, so diode is basically a non-linear component. Well, the resistance, we basically just said P equal to R times L. And so what it means by linear is that if I double the voltage, my current will double. Similarly, for a capacitor, if I double the voltage, although that there's going to be some time component to it, current will essentially double. But in the case of the diode, that's not quite the case, because it kind of depends on the direction diode as well. That's why it's known as a non-linear component. So this basically allows only flow in one direction. So the case I've drawn here, so basically the current will flow this. So the current will basically flow in this direction, and in the case of the flow, this is actually analogous to like a one-way flow control valve. So the other component, which is very related, is what's known as an LED, a light emitting diode. So here, the symbol basically just has two arrows in it. So yellow, I basically denote that it's a light emitting diode, but nonetheless, it has essentially like a longer lead, shorter lead. The longer lead is typically is positive, and then it depends on the diode. Sometimes it has a flat on one end, also denote the negative side. So generally the voltage drop across a diode is around 1.8 to 3.3 volts, and generally for the red LED it's 1.8 volts, and then for the blue it's about 3.3. So generally the voltage kind of rises frequency of the light that's being emitted. So generally what happens is if you had actually like a multicolored LED, so you'll actually notice that the red LED actually lasts a lot longer than the blue and the white and all of the other colors, because it actually requires a lower voltage to function. So the brightness of the LED, so that is determined by the current flowing through the LED. So generally you might have currents in 10 or 20 milliamperes common. And so what will actually happen is, because you know the voltage that's required by that particular diode, then you know the current based on the rating of the diode, you can actually calculate kind of a resistance that you need to add to that particular circuit. So let's just do that like a really simple example. So typically you would arrange a circuit as shown here, where you have a resistance in series with the diode. And so since we know the voltage drop here, we can calculate the resistance that we So the resistance would need to drop the rest of the voltage. So let's take a simple example. So assume that we have a 6 volt battery, and then it needs to drive a diode which is dropping 3.5. So the white LED actually has an even higher voltage requirement. So assume it's a voltage drop of 3.5 amps, 3.5 volts, and then you're driving it with a 6 volt battery. So what that basically means is the battery, so if you imagine it, so the battery has a voltage of this much, the diode has a voltage that can accommodate this much, and then you need to kind of like figure out a way to drop or dissipate this amount of energy. So what's actually happening is, because of the way the diode is designed, it's non-linear. When even if you increase, so if you increase the voltage across the diode, the current will just keep going exponentially, and then eventually what will happen is you will burn the diode and then it will just fail, and it doesn't really drop any more voltage than the rated voltage over here. So that's the reason you always need to have a resistance in series with the diode over here. So if you look at this, so what this means, come back, is that we need to drop 6 minus 3.5 volts across this resistance, and so that gives us V equal to IR. Then if we do calculation, we see that it needs a 250 ohm resistance in series for the whole circuit to work. So this is one of the very simple examples what how you can actually calculate the diode rating and so on. And then so instead of this 250 ohms, if you increase it to say 300 ohms, so what will actually happen is, if you do the calculation again, so you'll notice that the total current flowing through the circuit is actually going to be smaller. And this is one of the examples you can try out and then see and calculate this value. So the next component or we'll be looking at is known as a full bridge rectifier. So the idea here is you take the diodes that we just looked at, and we are basically going to be putting 4 of those in this square pattern over here. So the idea is, what's happening, this input is going to actually be a sinusoidal input. You wouldn't typically directly connect it to the power source, actually have a transformer to reduce the voltage, but just imagine there is like a sinusoidal wave that's coming in here, and then you have this output over here. So what will actually happen is, so imagine this is plus and this is negative for the options given over here. So red would be a positive and then the blue would be negative. So imagine, so you have an AC signal going over here. So imagine this point here is positive and the bottom is negative. So what's going to happen is this one is going to be conducting properly. This diode is also correct direction. So you can actually reorient the page and then verify this is the case. So what that happens is 1 and 3 diodes are going to conduct. And so then the output here is going to be positive, and then this is going to be negative over here. So let's look at the case where this point 1 is negative and the point 3 is positive. So in this case, the current can actually flow this way and then go to 4 and then go back to the plus and then go down here and come back in this direction. Notice that my laser pointer is moving in the direction of the diode arrows. That means they were actually conducting in the direction. So when the voltage is negative, the diodes 4 and the diodes 2 are going to conduct, and the output nonetheless is going to produce a positive at this pole and the negative at the other pole. So what this basically does is, irrespective of the sign that you're actually having over here, the output is always going to be positive here and then negative over here. So if you think about it, so what's actually going to happen here is that, so if you think about it, so what's going to happen here is that this pulse over here, this is going to be positive over here, and then if I use the same color, even though negative here, still going to be positive on the output of the diode. If I connect all of these, so you're going to get this pulse and this, because the sinusoid is going to be the repeated sequence of the stop and the negative, and then the positive and the negative pulse. Each of those gets rectified, and the output is going to look something like this over. So it's going to look something like this over here. So you just kind of like flip all of those sine waves, and then you're going to get a rectified signal, which is going to be a full wave rectified symbol over here. So let's next move on to printed circuit boards. So generally an electrical circuit is a closed path for the electrons to flow over here. So this is kind of a very simple circuit. So we kind of discussed this already, where your electrons flow from one direction, bulb, and then out to the other. And this is a simple thing that can be drawn by hand. And so you can actually create a more complicated circuit, what's known as a printed circuit board. So this is like a what's known as a breadboard. So where you can actually connect. So the way this is drawn or this is created, that all of these pins along the width are connected. So these pins are connected. These pins are connected. So this pin to the left and right, these aren't connected as such. All of these are connected and all of these are connected. So if you put different components, so what can happen is this wire actually gets connected to this point over here, which is actually this switch over here, and then this point is actually connected to the other side. So you can actually kind of create like reasonably complicated circuit, but not super complicated circuits over. So the way these are designed is that this distance between these two pins is typically 0.1 inch. Similarly, the distance between this pin and this 0.1 inch. So these are known as DIP components, dual inline pin. So this is an integrated circuit. So I'll kind of quickly go what an IC is in just a little bit. But nonetheless, so what's happening here is that this distance is going to be 0.1 inch, so that you can actually fit it inside the breadboard. And so what you can also do is the gap between the center, between this point and this point, is 0.4 inches. And generally, so what we do is we can actually assume that the capacitors that are made, you can either set the resistance like this, in which case it's going to be 4.4 inches, or you can actually twist and then have the resistance sit vertically, in which case you can assume it to be 0.1 inches. So these are two options you get. Actually select the resistance. So we can actually create more complicated circuits. So this one is known as a printed circuit board. So in the previous case over here, all of these wires need to be wired manually. So obviously this is not going to be great for your computer. So imagine kind of like shake your phone or your laptop and two of these wires fall apart and then it stops working. That's not that great. And it's also going to be fairly expensive to wire all of these. And this is actually a very simple circuit. So as it gets more complicated, you can't physically wire all of these on a breadboard. So in this case, what we do is we resort to printing it, where it makes it easier to mass manufacture those wires over here. So when we print all of these, so this is typically printed onto a non-conductive something like a fiberglass board, and the electronic components can be stuck or soldered onto the ones over here. So here, this is one of the example here. There are thick standards. So typically, based on the current that the component is going to consume, so if it's going to be for about less than 0.3 amps, so you use a 0.01 inch trace. For 1 amp, you use 0.05 inch trace, and 0.15 for 6 ampere trace, and so on. The other thing you want to do is when you have wires, you typically don't want bend those traces by 90 degrees. Typically, if you want to bend 90 degrees, you do 45 here and 45 here. So that's also useful when you're trying to print the traces in the circuit. So this is the component of the integrated circuit. So what you typically have is you basically have a more complicated circuitry here, which is all fitted inside one chip, and then which can actually get soldered onto PC that we just discussed. So an integrated circuit or components, basically you only need to connect external power resistance to that pin, and they have a lot of circuitry inbuilt inside the circuit. So then what happens is you basically have something known as pin out, and they will typically give you the circuit that you would draw and then how you would connect these. So here, this top one is known as a through, where you solder and then put the solder on the bottom, and then this is known as a surface mount soldering, where you put the components on the surface and the solder is actually going on the top of this component over here. So these microchips are also known as chips. Typically, we have the dual line pin, which is the top one, where the pins are spaced zero point 0.1 inches apart, and then this width is larger than 4.4 inches. Bottom over here is known as surface mounted integrated circuit. And so what actually happens is you can get the same component. So the number tells you the function of the integrated circuit. You can get the same component either as a top dual inline pin or a surface mounted component. So based on the circuit that you're designing, switch from one to the other. So typically what will happen is your data sheet will give you numbers, pin numbers, and what you need to connect to them. So here typically there is a dot on the integrated circuit, and for dual inline pin you also have a little small notch, and then you keep the place it as shown in the figure. You can start counting, and this pin is labeled to be number 1, 3, 4, 5, 6. So you kind of go counterclockwise. For the surface mounted, the bottom left corner starts 1, and 1, how many other pins you have. In this case it's 8, so 1 to 8, 9 to 16, and then 17, so on and so forth, and then you kind of go all the way around. So this is pin number 1, and then this way, and then similarly for this circuit over here. So the reason we need to know that is typically what will happen is the data sheet will tell you connect, say, a power source to pin number 1, and so you need to design your integrated circuit and the wiring so that you can actually get a power to this point, and then you can maybe connect a resistance to 2 port. They'll typically give you the numbers, or they might rearrange, and you basically trace the circuit based on the numbering that's done in on the chip. So let's now start looking at some simple problems in electronics. So here what we have is we have a chip called an MSP430, which is a microprocessor. So just like you have an Intel processor in your computer or your laptop, or an AMD processor, a microprocessor is a smaller version. So it's kind of used for data processing and data acquisition. And so MSP430 happens to be one of the microprocessors. So the data sheet, I've read it, tells me that I need a 3.3 volt supply, and it draws 200 microamps when it's running. So what we need to do is just as we did for the previous example and for the LED. So we are driving this from a 5 volt supply, and then we need to figure out what the biasing resistance needs to be, and then what also happens if there is a spike in the resistance over here. So you're going to assume that there is a sudden spike in the power current consumption of 100 to 300 microamps, and then you want to see what is the voltage change. So let's look at the first example. So in this case, the R needs to be V in minus VL divided by IL. So this is 5, 3.3, 200 micro, so 10 to the minus 6. We can actually calculate and then figure out what the voltage is going to be. So this is fairly simple, and then you substitute in the numbers, it comes to 8500 or 8.5 kilo ohms. Typically you just put 8.5 K, and because it's a resistance, you know that it's going to be in ohms. So let's look at the second example. So you're using this 8.5 K ohms in series, and then the current changes to 300 microamps, and then let's see what the voltage is going to be across the MSP430. The second case, it's the output minus I load 2 times R, and then you substitute V in is 5, I load 2 comes from here, which is 300, and then the resistance comes from the first step, which is 8.5 kilo ohms. And so let's do the calculation and see what happens. So in this case, you substitute in the value, and then it comes to 2.45 volts. So essentially it needed 3.3 volts, and it suddenly jumped to 0.45 volts. So let's do a follow-up problem where you're basically doing essentially you have a 10 microfarad capacitor that's charged 3.3 volts, and we want to see what happens when there is a current pulse of 100 microamps lasting for 10 milliseconds, and then how much the voltage actually drops. So if you're going to make this assumption here that the dV over dt is approximately equal to delta V over delta T. So if we recall, the formula for I is C dV by dt, and then we're going to approximate it as C delta V by delta T. And so then we want to find out what the delta V is based on all of this change. So let's calculate, and the delta V, let's calculate. So you're going to rearrange the term and then figure out the value. So I'll rearrange. So we basically find that delta V is I delta T by C. And so we substitute I is coming from here. Excuse me. So I coming from here, 100 microamp pulse. So that's the current or change in current. And then it's lasting for 10 milliseconds, or 10 to the minus 3. And then divide by 10 to the minus 6. This comes to 10 times 10 to the minus 3, or 10 millivolts. So notice you happen to use the same capacitor in the previous example, your current pulse is going to be much smaller. So let's look at few more examples. So what is the effective resistance of a 1 kilo ohm connected with a 2.5 kilo ohm? Then what is the effective resistance if they are connected in parallel instead? So the effective resistance is R1 plus R2 for series. So let's pause the video and then do the calculation. This comes to 1 plus 2.5, which is 3.5 kilo ohm. So for the parallel case, so we basically have 1 over R effective is 1 over R1 plus 1 over R2. And you can once again pause the video, check the values, and then you find this comes to rearrange. This comes to R1, R2 by R1 plus R2. Then you substitute in the values. This comes to 0.7142 kilo ohms. So let's go to the next problem. So where you have in 3.3 button cell, and then it's driving a 1.8 volt red LED, and then we want to figure out a resistance in series to limit the current to 20 milli. So this is very similar to the problem we already did. So you can again pause the video calculation. So basically we do essentially V supply should be equal to the resistance plus the LED. So V supply, and so the resistance is going to be V, R is R times I, and we can substitute that. So this V supply should be R times I plus V LED, and so R should be V supply minus V LED divided by I. This is the formula that I gave you before. This kind of gives you the derivation. So we know V supply is 3.3, V LED is 1.8. If we substitute in the values, we get 20 milliamps. So we get 3.3 minus 1.8, and by 20 times 10 to the minus 3, then this comes to 75 ohm. So let's look at a follow-up example. So the same LED from the last problem, 1.8 volts, is connected in series with a 100 ohm resistance being powered by a 3.3 volt button cell battery. So here the resistance is given, and what we are trying to do is calculate the power consumption, power being drawn by from the battery, the current consumption, the power from the battery, and then the fraction of the power being consumed by the resistance and the capacitance. So you can kind of redo the calculation, and to calculate the power, what you would do is multiply the voltage with the current. That will give you ampere volt or volt ampere, which is the same unit as watt or power, and 10 to the minus 3 watts is actually equal to 1 milliwatt. So milli is 10 to the minus 3, and then you can actually do the calculation and continue the video. So just rearranging the term, so V supply should be equal to IR plus V LED. So in this case, so what we don't know is the I. So we can kind of like rearrange this term and then write it as V supply minus V LED by R equal to the current, and then that becomes 3.3 minus 1.8 by 100, which comes to 15 milliamps. And just as we said, the power in any component can be calculated by the current times the voltage over here. So how do we do that? So power of the battery would be 15 times 3.3, should be 49.5 milliampere times volt, which actually comes to milliwatts. Similarly, resistance in the power through the resistance is 22.5 milliwatts, and then the diode is 27 milliwatts. So this 27 milliwatts here is the one that's actually being produced as light. So if your diode is 100% efficient, so it'll actually be producing 27 milliwatts of light, equivalent light. So if it's, say, a little bit less efficient, like 80%, then you'd be producing 80% less. So you basically convert that power to lumen, and then you can get the brightness. So if you come back here, so that means that the power, this is the total power consumed by the battery, and then you can look at the power in the diode. It's going to be this divided by this, so that comes to about 45.45 being spent in the resistance, and the rest 54 point something, 50.955 would be the percentage or fraction of power that's basically being supplied to the external circuit. Okay, so next we're going to be looking at kind of creating a manual PCB. So the figure I've shown here is known as a schematic. So these are basically symbols that we use. So here, so notice that even though the wires are crossing, because I don't have a dot, means these are actually not crossing each other, so they appear it. You actually have a gap in the third dimension. So here what we've done is this symbol here, so all of the symbols here are assumed to be connected together. This upward triangle, this is assumed to be connected to here, and then this denotes that the voltage positive supply, often denoted as V plus or VCC, and then this is assumed to be the negative of the battery or the ground, and then we're assuming all of these are connected. So the circuit I have here is what's known as an operational amplifier. It's known as a non-inverting amplifier, and we can actually look up the data sheet. So if you do that, this is the circuit that's given, and then we're going to create the manual PCB for this particular circuit. So if you look at the actual component itself, so you will notice that so what I did was I basically went and Googled operational amplifier. Since I actually know the circuit itself, I actually downloaded the data sheet. So this one is from Texas Instruments. So what you can actually do is, so once you have some background on circuit, you'll typically know some circuit numbers, operational amplifier, or you can just search operational amplifier circuit and then look it up. So in this case, what happens is the way this is denoted is that 741 denotes the chip or the basic architecture of the integrated circuit, and then LM here stands for the manufacturer. So typically, chips manufactured or the circuits and integrated circuits manufactured by Texas Instruments usually have a letter LM, and the 741 is the type of operational amplifier. So similarly, you might have something known as OP741 that's manufactured by somebody else, and so on and so forth. You can actually look at all of these applications over here, and it tells you different grades, and this gives you the different packages that are available. And so you can look at all of the stuff. This gives you the typical layout of the application. This actually gives you a lot of specifications over here. Tells you application and the example. So this is the example circuit, physical layout, and this is kind of the schematic as to how things are actually connected. And they will typically give you, so if you scroll down, it will give you all the specification, minimum, the maximum voltage, the temperature ranges, supply voltage, and what needs to be done. So you can actually Google LM741. Then you might have typical variations. So this is LM741, this is LM741A, and so on and so forth. These might have, and then this is 741C. These would have slightly different specification, but the basic application would be the same. This gives you kind of like a simplified circuit or a block diagram. We're not going to look at that either. And then this is the example that I basically have. So the symbols for V plus and V minus are a little bit different, but nonetheless, we can kind of like use the circuit. And then it also gives you the frequency range, typical layout that they recommend for an example layout as how things need. So nonetheless, so this one doesn't really have a pin associated with it, but you need to go back drawing and then it'll tell you how the pins are actually laid out. Here it tells you this is null offset, this is converting and so on, and then based on that you need to map it and then figure out how the circuit is looking. But in our example, I'll actually give you a layout, very simple, a simple layout. Like so here, and then you'd be asked to create circuit over here. So what we're going to assume is that when you have resistances, we would assume they are 0.1 millimeters apart. So you're going to assume that the resistance are mounted vertically, kind of like fold the resistance and put them in. And also you can put them 4 millimeters apart if you want. And then the pads are generally, so what happens is you have like a gray outline to denote, and then generally you have pads where you have the wires being connected to the component over here. So if you do that, so I can assume this is the way I would create the circuit and then create like a manual PCB for this. So let's switch here to the document screen and then do like a manual circuit board. So just a quick note, so we wouldn't be needing too much space, so you could have written stuff here and so kind of like had some notes regarding the size. The other important thing to note is we want to make sure that the wires don't cross. So we're going to essentially we draw this for the resistance. Basically denotes a resistor or capacitor. So whatever component you would need. So this is assumed to be say 0.1 inch, which is going to be about the same distance between pins. And this is assumed I spaced it, so this is about 0.4 inch. So obviously I've scaled this up several times so that you can actually create the drawing, but you're going to assume that when you create it, it's about the same distance over here. So if you have a wire, have a single line like this, so this is going to be wire. And so what will happen is if you have a wire, then you're going to have a trace, and this might be connected to one of the components over here. Then you might get the wire from the outside, solder it over here, and so this is like a physical wire that's coming from outside and then soldered over here. So in our circuit board, we're just going to have like a pad or a wire pad over here. So the other thing to note is we want to make sure that your traces never cross each other. So this is actually wrong, because if you actually were laying this out in a circuit and then they cross, there's going to be like a short circuit that's created over here. Even though in the schematic the wires might cross each other, for instance over here I have the wire crossing, but this is not a physical contact, but physically if you actually had wires cross over each other, that's going to create a short circuit. So the other thing to note is if you want to bend something by 90 degrees, so we would use 45 degrees. So we want to avoid this wrong, and we want to avoid like wires going like this. Avoid this. So the reason is when the wires are fairly thin and then they try to manufacture this, there might be like a missed connection. So what they recommend is basically doing 45-degree connection. So the preferred way, instead of bending by 90 degrees, you bend by 245, get the same effect, but it makes the connection actually more robust. So let's look at the circuit over here. So notice that they seem to be arranged haphazardly. So what is actually happening is if you look at the circuit over here, so what's actually happening? So just reduce the brightness a teeny bit. So here, this point is actually technically connected. So you're going to assume that this is connected to here, and then this is connected to here, and then actually connected. So all of the similar symbols are connected, and then these ones are actually wires, and then these ones are wires connected. So the easiest way to do is kind of go look at the pin number that's denoted over here and then try to match them with the pin number at the bottom. So pin number 1 isn't connected to anything. Pin number 2 seems to be connected to this joint over here, and then to R1 and R2. So let's try to do that. So pin 2 is over here. So let's maybe pull this wire out. And then we're going to create resistance over here. So for the resistance, I'm going to put wire blocks. So this 1, 2, to resistance. And then typically what happens in the printed circuit board is you actually have what's known as a mask or a layer where you can actually create letters. So if it's a more expensive board, you can actually have letters. So we'll assume that. So this is called R1. And then this is R1 is connected to a wire input. Let's extend this further to create our wire input. It's going to be a simple pad. Then you're going to assume that the wire is connected and then soldered. This point over here. So this is going to be called W in. So we have this, and we have to connect this to the R2, whose other end is connected to 6. So R2 and then the other end goes to 6. That seems to be like a long way around. So let's maybe just pencil this in. So it's connected to here, it's connected to here, this gets connected to here. So I put a very faint line. So I want to make sure I have enough space to connect all of the other stuff. So we come back to this. So let's go to the next pin. So 3 is connected to ground. 3 needs to be connected to ground, and 4 is also connected to ground. There's nothing else, and then there's battery. So nothing else is connected. So what I can actually do is connect these two directly. And since I don't want a 90 degrees, I can just do 45 degrees like so. Wire here. And we'll just call this battery minus. And let's go to taking care of 3 and 4. Let's go to 5. 5, my circuit isn't connected to anything. 6 needs to be connected. So and it looks like I wouldn't be in too much trouble if I connect this wire here. So let's do that. Down. And this is going to be bending by 45 degrees here. Right. Then 6 is going to be connected here. And 6 also needs go to an output wire. So bring that. Take care of that in just a bit. And so you notice that it might actually be easier to connect it like this. So I'm going to put my wire and since I need to get a W out here, so I can either do a 45 degree and make it more complicated, or I can simply connect both of them at the wire out. So maybe just wire out here, connect the 6 over here, one here, and just label this W out. Let's go to here. So W7 or the pin number 7 needs to be connected to battery in, and so let's send this out and then put wire connection here. All this battery plus. So if you're connecting a actual battery, so you might need to do something more clever. So what you could have done is actually have this go underneath the circuit, and so then there's no crossing, and then you can get both of this battery and put like a battery block over here that is going to power the circuit. So this is the simple layout. So this is actually known as a single layer PCB, where we put all of it on the same surface. You can actually have, for more complicated printed circuit boards, you can print one on the top and one on the bottom, and then you can connect both of those surfaces. So you assume when you have a wire, like a hole, you actually put like a copper or a tin plating, so it actually connects and that will actually connect the top and the bottom wire. So if I basically have a wire at the top like so, and then I have another wire at the bottom, maybe at another angle, and I have a through hole, those are actually connected. Otherwise, because the board itself is actually insulating, the top and the bottom layers actually aren't connected to each other. So let's maybe just quickly check if we have all of the components connected. So double check. So pin number 2 is connected to one end on R1, and the other end seems to be connected to R2. We connected to R1. Then look. Looks like we're missing R2, right? So this is one way you can quickly identify the problem. And so you can either put the R2 over here, or anywhere you want. So maybe we can put the R2 bottom here, matter. Put pull here, and then we create a similar kind of a silk outline for an R2. Call this R2. So this is actually optional, kind of creating the surface around it is optional, but it just makes it look nicer. So then the other end of R2 is connected to here, and it's connected to output. So this is connected. So we're done with our this and here. Let's go to pin number 3. Pin number 3 here is connected to the ground. So pin number 3 is connected to here, which is actually the battery minus. Then it's connected to the battery minus to pin number 4 as well. So this is good. Go to pin number 5. It's nowhere here in the circuit, so it's unconnected. Pin number 6 is connected to the other end of R2 and W out, so that's taken care of. And then go to pin number 7, which is over here, and then that's connected as well. And then pin number 8 is not connected. So we can do the same thing for R1, just as a sanity check. So one end is W in, that's good. The other end goes to pin 2 and the R2, that's good. Go look at R2, connected to pin number 2, that's connected over here. And then the other end goes to 6 and W out, so that's good. And then battery in is directly connected here, 7, then battery minus is connected over here. So our circuit is basically good, and then we're also ensure that no wires are actually crossing. And then anytime you need to do a 90-degree bend, you're ensuring you have like a 40 or a 60-degree bend, and that's the way you basically make the circuit. So this concludes our video on basics or introduction to electronics with respect to MSE100. So just note that the circuit design and electronics are going to be much broader. So you need to have a fairly extensive knowledge about the different circuitry and then how chips perform and all of those stuff. So those will be covered later on in the mechatronics program. But this basically gives you a very, very brief introduction to how you would create an electronic circuit and kind of like a brief introduction to the various component, and then how you would create a single-sided PCB using just like a manual drawing. I do have an addendum video which discusses how you would use a software called as an Eagle PCB software that you can use to actually create a similar drawing, or in fact if it's a more complicated drawing, typically you might look at a data sheet and then take the example circuit and create circuit that you need in the software and have it manufactured either at MSE, or you can have it shipped and then manufactured by somebody else. So thank you everybody, and see you again later.